Hello YouTube, welcome to my tutorial where we talk about reinforcement learning models. Now this is another tutorial, part of the many other tutorials that I've done already. I've done a tutorial on supervised learning models. I've done also a tutorial on deep learning models. But in this video, we are focusing on reinforcement learning models. All right, what is reinforcement learning? Reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with the environment. The agent takes actions, receives rewards and penalties, and updates its strategy over time to maximize its rewards. Reinforcement learning is widely used in robotics, in gaming, in financing, and in many other AI driven applications. Basically, what reinforcement learning does is like you training your own dog. If your dog do what you want it to do, you give it a treat, a toy, attention, praises, and anything that allows it to continue to do the behavior that you want. On the other hand, if the dog behaves in a way that you don't want, you either walk away or you do not give it any praise or any petting to the dog. Over time, the dog will realize that this behavior is unwanted and this behavior is rewarded. So that will be your negative and positive reinforcement. There are about 5 or 6 key components when you are talking about reinforcement learning. First one is agent, which is the decision maker, the environment, which is where the agent operates, the state, which is the current situation of the agent, action, the choices available for the agent, reward, feedback received from taking action, policy, the strategy that maps states to actions, value function, which is the expected long-term return of the state, then the Q value of the Q function, which measures the expected future reward for taking a particular action in a given state. In this video, we are going to focus on Q learning. Now, Q learning is a value-based reinforcement learning algorithm where an agent learns an optimum action selection policy using a Q table. The Q table, in our case, stores the expected reward for each state of action and updates based on the Bellman equation. I don't have the Bellman equation with me right now, but you can Google it up and look. It have got um, the symbols that you can that comes up to the formula, the equation. All right. So in our example, we want to traverse the frozen lake. I have just outlined it here. We want to traverse the frozen lake, which is this lake that you see in the background here. And we have our Q table, which is this table. So we want to train an agent here to traverse from the start, which is S here, all the way to the end. We don't want it to traverse to this H, which is the wall highlighted in red. Just like a human being traversing a frozen lake, we want a person to come from this end of the lake to the other end of the lake without falling into the water. Same thing in our case, we want our agent to traverse this grid from start to finish without going into these holes. So in our example here, the agent, they've got options to either go this way, go this way, go this way, or go this way. So we gonna train our agent, and if it falls in H, it's gonna be punished. But it goes on F, which is safe route, it's gonna be rewarded. Then we'll see how it's gonna get to the end. So this is our project that we're gonna start on. I am going to head on to my Jupyter notebook to get started. All right, now I am in my Jupyter notebook. So let's go ahead and start this project. So in this project, we want to train our agent using the Q-learning to navigate the frozen lake environment. We wanted to find the best way to start from the end to the finish. So the agent must learn to navigate to the end, from the start to the end, while avoiding those holes, and also to maximize the cumulative reward. And like I showed you earlier, that frozen lake environment is just a 4x4 grid. We're gonna start from the start, and it will find the best optimal way to navigate from the start all the way to the end. All right, so our goal is to using Q-learning for those. FrozenLake is an environment given by OpenAI that we can use to train. So to maximize rewards. And we are going to use, in our case, we are going to use the FrozenLake environment. All right, so I'm going to take this one to Markdown, run it, and let's go start ahead and import our critical libraries. So in this case, I would want NumPy, I would want Gym, I also would want Matplotlib and Seaborn. So NumPy, I would want also Seaborn. So Matplotlib and Seaborn, SNS, I use them for visualization. Okay, NumPy is a library for numerical computations, especially when working with arrays. In our case, we are going to work with the Q-table, so automatically we are going to use NumPy. Then Gym is that's the OpenAI AI toolkit for developing and evaluating reinforcement learning algorithms. In this case, we are going to grab FrozenLake from that environment. And again, Matplotlib and Seaborn, I'm going to use it to uh, to visualize. So what we want to do here is to create the FrozenLake environment. So to do that, we're gonna do environment is equals to then our gym dot make, and we're gonna just specify the name here, FrozenLake, which is in our case our version 1. It's a string. Render mode. All right, let me explain this one. So gmake gmake, what it does is kind of initialize the FrozenLake version 1 environment. So as I said, is slippery to false. It ensures that the environment is non-slippery. In the original version of the environment, the agent movement might not always be predictable. So, but with setting is slippery to false, the agent action would oh my goodness, the agent action will deterministically lead to the next state. Actually, when it's not slippery, it will allow the agent to traverse to the next step. Now I've set the render mode to ANSI. It actually specifies the text-based rendering of the environment. We're gonna use it's very useful when we do what you call console visualization. All right, so now I've done this. I want to initialize my Q-table. Q-table. Right, to initialize the Q-table, I want to specify the state size. All right, state size. So our environment observation action perfecto. Let me do this. Actually, I need to do the other way. I can just delete this one and do this one. Yeah. So that I can have more space and push it up on the middle of the screen. Alrighty. All right. What do I need to do here? My Q-table. All right. So what I need to do here, or what you need to do is to have your state size and action size here. So what we are doing here, we want to retrieve the total number of states in the environment. In our case, I've shown you this, the diagram. There's 16. It's a grid of 4 by 4, so there's 16. And uh, the action size, we want to retrieve the total number of actions the agent can take. So remember, if you do I still have it right here? All right, I closed the PowerPoint. But remember, the agent can traverse up, down, left, and right. So our Q table, now, if you see here, good catch. All right, so our Q table now, um, we want to initialize it one with dimensions of state size and action size, and fills it with zeros. The Q table will be used to store the Q values, which represent the expected future rewards for taking a given action for the specific state. All right, so now that we have initialized our Q table, we need to specify our hyperparameters. All right, to specify our hyperparameters, we have to have our learning rate. In our case, I wanna do 0.1. If you look at the Bellman algorithm, this will be the alpha parameter. Let me see if I can quickly Google it. Go rhythm. Let me see. Yeah, this is the one. So, oh, I went to YouTube. Let me. Oh my goodness. But anyway, I closed it. Let me see if I can pull just a quick image. There you go. So now when we are setting our hyperparameters, we are actually doing this equation. All right. So the alpha, we are going to do the discount factor. We are going to do the epsilon max mean, and also we're going to do the decay, the episodes, and the max steps. All right. Let's go ahead and go back to our parameters. So discount factor, I'll set it on 0.99. 0.99. Alrighty. Let's do which is my initial exploration rate. Epsilon mean 0.01. This is the minimum exploration rate. So this one is the initial and this is the minimum exploration rate. Then let's go ahead and do the decay. I want to set it on 0.995, which is kind of a decay rate for each and every episode. Let's go ahead and do the episodes, which is basically the number of episodes. Max steps is equals to 100. Now, if you do not set your max steps, the agent will keep on traversing that grid. It will be like a while loop. It won't really stop. So we want to stop at 100. All right. You can set it of whatever number you want here, but I think 100 is a good uh, so that it won't keep on. It will be an endless loop. We don't want that. All right. So let's go ahead and track the rewards. So I'll start with an empty list here, which is I would call a reward list. I'll just initialize it at 0. Then I want to count what I call success count. It will be start at 0. All right, so I'm going to use that. So let's do our Q learning training here. Alrighty. So to do our Q learning training, what we need to do is I can do a while loop. Actually, let me go with a for loop. All right, so I'll use for episode in the range all the entire episodes. All right. Our state is goes to environment. And want to always reset that environment. Then our done, I want to set it on false. Then our total rewards, total reward. Right now, initial, it will be on 0.0. Then I want to go again for step in range. Again, I'm going to provide this code in my GitHub. There will be a link in the description for my GitHub, and you can take it from there and modify it, play around with it the way you want. All right. So for step in the range max steps, what do we want to do? So I would say if run here. All right. Then action. Actually, dot action. In our case, action space here. Then else action my Q-table here. I want state and everything. I'm kind of I want to set the best action. All right, so now that I've done this, I want also to perform the action. So what I'll do is to do next state of my reward. Next state reward. Done. Is equals to an environment step, then this will be action. Alrighty. So um, if done and reward is equal to 1, what do I want to do? Then reward is equals to 10. I'm just rewarding the agent with 10 points. Then success, which is my initial variable, success count, I want it to be added with 1. Then elif done and reward is equals to 0. There is no good outcome. What do you want to do? Want to punish it, right? So reward is equals to -5. We are kind of penalizing the agent for falling into the holes. Remember, we are traversing the Q table. All right, um, so what do you want to do? We want every move that is happening, we want to update our Q table. So here is what we're gonna do. So under this for loop, we want to go ahead and do Q learning, update rule. So it will be still under the action. So our state and action. Alrighty. Okay, Q table state action is equals to, then we're gonna do 1, the learning rate, we want to multiply it action. Let me edit here just for a new table, and okay, let me push it to the next learning rate times, what do we want to multiply it by? We want to multiply it by reward, and also reward plus, I will say, my discount factor. Let me double check on this one. Yes, I want to multiply by discount factor, and also multiply by discount factor. Then, okay, Q table, then next state. All right. And again, I'm gonna add to this total reward. I wanna count the rewards, then state. Alrighty. Yep. State is equals to next state. Perfecto. So if done, what do I want to do? I just want to exit, so I'll break. And now again, we want our agent to explore. We want to explore when we initialize our agent. We want to explore, but over time we want it to pick the right pathway. So we want to lessen the exploration over time. So to do that, what I'll do is so my max Mhm. Let me think here. Okay. I want to append this one to the total reward. All right. Let me see. All right. Perfect. So now I will let me go ahead and print the progress. So node 1000 is equals to 0. What do I need to do? I just want to print um, my f string here, episode. Then I want to grab the episode and my total reward is equal to total reward variable. Then I also want to print the success rate is equals to, let me, all right, it's success count here, divided by the episode. Hmm. Then I want to format it perfecto. All right, so the rest here is just I want to visualize to have that the Q-table. I also want to visualize the rewards. So let me go ahead and visualize the Q-table. And again, I want to visualize the rewards. All right, let me start with the Q-table. So plot.figure, you specify the fig size, whatever size you want, doesn't really matter. So I'll go with an 8 and 6 here. Perfecto. I want it as a heat map. So the entire Q table the width of the lines doesn't matter, 0.5. Then the labels, all right, let me start with the X label. This will be actions. This will be against the stats. Yeah. And my title, it will be Q table heat map. Actually, let me also visualize the rewards. So to visualize the rewards, what I want to do is plot figure, my fig size is equals to whatever size that is comfortable with you. The smaller the better. In my case, we want my reward list. the color, whatever color you want, blue. I'll set the alpha to 0.7. I'm gonna plot the X label. This will be episodes. Episodes. The Y label will be total rewards, and my title it will be, actually I don't want total rewards in this case. Okay, total rewards. Yeah, reward progression over time. Then I just want to show this one. Okay, we don't need this one now. Dot show. Perfecto. All right, now let's render. Wait, okay, let's test the trend agent. And so my environment, which is gym.make, what is its name? It's FrozenLake. FrozenLake, and it's version 1. Perfecto. I set it on is slippery. I set it on false. The render mode in our case here, we said it was set it on 0, and also currently done is set on false. Let me print the agent navigation. Agent navigation. Yeah, I can do that. I can just set it on a new line. Okay. While it's not done, action np we say is equals to my environment. Alrighty. Right, let's do, what do I need to do? I want to print the environment. And also just environment and close it. All right. The meat and bones of my Q-learning is done. Alrighty. Let me run and see what we got. Oh, perfect. I thought I had several errors. Okay. All right. And also Alrighty. All right. It's not. I'll change the color here. Okay, let me also look right here. I can go with blue. I said cool on instead of cool warm. And also I will check the other errors. All right, what is it saying? Oh yeah, oh yeah. Let me just go back to and run. So what I'll do is I will also check the errors and see if it looks like it's stuck on the start. It's not traversing. It's not traversing. So it's if you remember that. Let me pause it and I'll see why is it stuck on the initial um, on the um, initial state. We want it to traverse the entire grid. All right. All right. So what I end up doing is I end up adjusting my learning rate and the discount factor, basically for better convergence, and also I also modify the Q table update formula so that for better learning stability. All right. So here are my results, and this the progress over time. It explores when it's starting, then it kind of knows where to go next. Then at the same time, this is my heat map, and I want to show you how it is traversing. So start, it went down again, it went right, down, and G. So something like that Q table that I showed you earlier on. Do I still have it close by? All right. But let me see. Yeah, I'll put it on the screen. Oh, actually, I can quickly put it up. All right. So what it did is it went down, down, right, right, down, and it took this route. Start F, down, down, right, right, down, and G. All right. So it went in an unknown environment, find the best way to traverse without going into these walls, and went all the way to the end. All right. Thank you for watching. I'm going to upload this code into my GitHub and see you on the next lecture.